Good morning, everybody. Thank you for joining us for today's webinar, which is going to be about the Agilent 990 Micro GC. So this is a dedicated gas analyzer that can be used in the lab, online, or in the field. Today's agenda, what we're going to cover here is essentially what a Micro GC is, having a look into the hardware design, and then taking a look at the various column choices and applications that the Micro GC can and has been used for, and then delving a little bit more into the configurations for what it means to have a lab instrument or the mobile or the process platform, and then a quick look through the software and the accessories, leading us on to a summary. So as we're going to start here about what defines a Micro GC, essentially, one of the first things that obviously comes up is the small and compact design. So the Micro GC has been based on the platform of conventional benchtop GCs, but using this proven technology and shrunken down really with MEMS technology, so micro electrical mechanical systems. So essentially means everything within inside this platform is very, very small. So obviously, footprint wise, dimensions, as I said, the Micro GC, as its name suggests, is very small. If you're looking at the typical chassis that we see here on the picture, it's really no bigger than a shoebox, measuring sort of 15 centimeters wide, 30 centimeters high and deep, weighing only 7 to 8 kilos. So a very, very compact portable system. But also environmentally, when we look at the footprint as well, certainly compared to your conventional GCs, um, the carrier gas that we use with here is about 10% that we would use typically for benchtops, and the power usage is much lower, just runs off of a 12-volt plug to come in here. So the power usage compared to conventional GC is obviously very different. In terms of speed as well, typical analysis times here are 1 to 2 minutes. We work isothermally for the Micro GC rather than heating up the columns with ramps to drive off our components of interest. We operate isothermally within here, so we've got very quick startup times, but no delay between analysis as well. And where it differs really from our conventional counterparts is that it's gas analysis only, with the exception obviously of LPG or LNG, which we'll come to later on. But this is a dedicated platform really built for fast analysis of gaseous samples. And it's an incredibly flexible platform, as we suggest here, that can be used as a lab tool. But it can also be used due to its size and compact and light nature to be out of the lab, but also to operate as a process platform as well. So this is where it really differs from our conventional GCs. We're not trying to compete against benchtops with this technology. It's really to fill a void in the market for applications, making this really a gas analyzer rather than necessarily a comparison to a bench GC. In terms of flexibility as well, we've got the option to work as what we call single channel or a combination of different channels up to a maximum of 4 within here. And it really is these the channels that are at the heart of the technology of the Micro GC itself. So each of these channels are made up of 4 key components. So the first part of the channel will be the gas control. So we have what's called a DEGC, so a dynamic electronic gas control unit. Now, the purpose of the DEGC is to control the flow of the carrier gas and the pressure, and to control the backflush element of the system as well. Backflush essentially is something we can use to remove a certain portion of the sample before it goes onto the analytical channel. I'll have a little bit more about that in the software, but the gas control unit is really controlling the gas and getting rid of any unwanted sample from the run itself. Then we have a MEMS-based injector. So this injector is, as it suggests, a very, very small, smaller than a postage stamp injector. So it's actually only 10 microliters in terms of its maximum sample loop. We've got temperature control up to 110 degrees here, based on obviously what the application would require. And instead of using volume, we use injection time, so that we have a very, very reproducible results, and that we can because we're working with nanoliters really of gas that's going to be going through the analytical portion of this channel. We've got very good control and very good reproducibility by using these micro injectors based with time. One of the considerations we do have to make with the platform in general is that it's maximum sample pressure of 1 bar. Because the platform is designed obviously for only gas samples, we really do need to condition the sample so that it is non-condensing, below 110 degrees and below 1 bar of pressure. We've got a lot of accessories to be able to do this at the front end before they're introduced into the micro GC itself, which I'll cover later on. But the maximum pressure that the injector and most of the other components can withstand is typically 1 bar. Then we have the column part, so really the sort of analytical and the separation part, if you like. So this is where we're taking traditional sort of benchtop GC platform, and we're using smaller columns, so shorter columns than you would in a benchtop, often narrow ones. So we typically work between 4 or 10 meter pack columns within here. They can either be straight or they can have a pre-column, which allows for this backflush functionality that I discussed. The column temperature, typically most of them can go up to 180 degrees, some a maximum of 160. Depending on the application that we're using, I'd say most of the methods are probably anywhere between 90 and 110 degrees where we have the columns within there, but they're all adjustable. But as I mentioned in the earlier slide, we do operate isothermally. So once the method is set at that temperature, we heat the column very quickly to that temperature, and it maintains that for the duration of your sequence or your run. And then after the column, we have the detector. So we work with a thermal conductivity detector in here. This gives us sensitivity down to really about 2 ppm for most of the samples, anywhere up to 100% of these gases, extremely linear and a fast auto ranging, whether we're working at a low concentration sample or a high concentration sample as well. So these components themselves are all interchangeable. Anybody that's familiar with the micro GC previous models like the 490 or the 4900, the columns essentially, or the channels, had to be replaced as a 1. When Agilent looked to redesign this system 4 or 5 years ago, one of the big parts was to make the components accessible for not just service engineers, but also for customers if we needed to change certain parts of them. We can now change each of those components that I showed you on the previous screen independently. So if an application changes, the column cartridge can be changed. If a TCD needs replacing, it's not the whole module that needs replacing. Same for the injector and same for the gas control as well. So there's a lot of smart connections on here that allow us, from a service and maintenance point of view, to have early diagnostic to figure out if what the root cause of anything could be, but also to us allow to planned or unplanned replacement of these module components, which obviously brings the cost of ownership down and decreases the downtime for you over the life of the instrument. In terms of the theory of operation, each of these channels are independent of each other. So if you had up to 4 channels, you would have 4 of what we're seeing here. So the carrier gas essentially comes in. We have the carrier gas set at 5.5 bar from a regulator or supply. And it'll come through the proportional valve and is controlled down to the pressure that you define for your particular method. So the carrier gas comes through and passes through the analytical and the reference side of the columns. We have the sample coming in via the sample path and through an injection control. So this is basically where we inject what we want to into this sample loop. And then once the sample loop from the analytical line is mixed with the carrier and the sample, we then have the path flowing to the TCD, so that we have an analytical measurement which contains the carrier gas with the sample, the unknown, and then we have a reference column which just contains the carrier gas. So what we're doing is measuring the difference on the TCD of the reference, the known, which is our carrier gas, and then the analytical difference, which will contain our sample. So the way we have to do this in terms of choosing a carrier gas is to identify the components that we want to analyze first, and then choosing a carrier gas which is going to give us the optimum difference in terms of thermal conductivity to allow us to work at lower ranges of sensitivity. So for instance, if we are looking at nitrogen as a component, what we're not going to want to do is use something like argon as a carrier gas because they have similar thermal conductivities. So in this case, we would probably opt for something like helium, which has a greater difference between what we're trying to measure and what we have as a known passing through. The helium is probably one of the more used of the carrier gases. Argon as well. The only difference that we obviously want to make sure is that we've got this greater disparity between what we're actually looking to measure and what we're operating with. In terms of the hardware itself, there's the option to have what we class as a single chassis, which can control or contain two independent of these micro GC channels, so one in the top and one in the bottom of the chassis. If we are looking at a configuration that requires a third or a fourth channel, we essentially will bolt on via a heated bridge a second chassis within here. In terms of the connections, we can have a carrier gas obviously that connects to the rear, and we can either have a carrier gas for each of the channels. So if you wanted nitrogen or argon on the first one and helium or hydrogen on the second, you can do so. If you have a dual cabinet, you can also connect up the carrier gases for there independently as well. So each of these channels can have different carrier gas. The sample will come in from the front and it will be split equally across these 4 channels. You can choose different inlets on the front, which we'll look at on the accessories for how we do the sampling. But essentially, they will run simultaneously, whether you've got 1, 2, 3, or 4 channels within here. We've got various connections on the back for communication. Typical operating systems will connect via Ethernet or LAN cable to a laptop. We've got different accessories for outputs for analog, digital, if we're looking at more of a process type system, but I'll cover these later in the slides. Then we've got the power supply, as I said, 12 volt connection in the back, and that powers both of the chassis if you have 2 of them within there. But essentially still a very, very compact platform, very, very simple, easy to set up. We essentially need carrier gas supply at 5.5 bar and then power, and then obviously your sample connecting up from there. In terms of column choices, there is a wide variety of column phases available. Some of the more common ones are things like the mole sieve, so for permanent gas work for nitrogen, oxygen, hydrogen, helium, CO, etc. There are various lengths of these available, so 4, 10 or 20 meter based on your application. And then there's various lengths of backflush pre-columns that we can add on to these as well. And then we have a variety of columns that can cover the hydrocarbons, anywhere ranging from C1 to C10. Really is dependent on what the customer is looking to do and what they're looking to analyze and what levels they're looking to analyze as to what configuration we would define in terms of the columns and the channels. As a brief and an overarching sort of look at what micro GC applications you can traditionally look to use it for, primarily natural gas and energy was always a big one for the micro GC and confirms to still be that as such. We'll have a little look at a couple of these in greater detail to show you the basic configurations and obviously what we can expect in terms of results from there. We've got environmental applications that we use. Very popular ones are certainly in terms of academia research, reaction monitoring, where we may look at fermenters, bioreactors, lots of different things. Essentially anything where you're looking to do the analysis of single or multiple components of gas can be considered here. So one of the applications that I'm going to look at is this mud logging exploration application. So there's obviously a lot of compounds found when people are drilling as part of the oil and gas exploration process. And it's critical really to identify the most producible zones for these oil and gas. And it needs to be a very rapid and sensitive method to ensure obviously that the mud logging is done in the correct positions. We have a ready-made application note for a lot of areas that we work with, and as mud logging is one of the key ones for the micro GC, we've got a 3-channel configuration set up and ready to go here. This covers emulsive and poroplot and a CP SIL column. So we're able to do permanent gases, CO2, sulfides, and hydrocarbons up to C8. And these can all be qualitatively analyzed within 40 seconds. So it's an incredibly quick method. And one that's very, very reproducible. So if we take a look at some of the results here in terms of retention times area, we are covering an awful lot of components across these 3 channels within 40 seconds. All of the data that we show in these slides as well are done with 10 replicates, so you can see how reproducible and stable the platform really is. Another key area for us is natural gas analysis. This is obviously a big source of energy. It's used for all sorts of things commercially, like heating, cooking, electricity, fuel for vehicles, chemical feedstocks. So it's a very, very important part of the global economy. And natural gas is traded on its energy content. So it's very important for the providers of this resource to have an accurate grasp on what the composition is. So really having the calorific value and certain other indicators as to the quality of the natural gas. As this is one of the very key areas for us, we've got a number of ways we can sort of tackle this, and it's based on obviously end user requirements. But typically we have 4 configurations that are ready to go out of the box. So these analyzers are provided essentially from our point of view as a single part number. So we would discuss which compounds components are of interest. That micro GC would come out with the correct configuration. It would come with a checkout gas that's already calibrated, and application methods that are already set up. So you can literally just turn the system on. It can be run straight out of the box, factory tested with checkout samples. All of the manuals, reports, everything there ready to go within minutes for you. In terms of looking at the reproducibility, again, we can expect something similar to this in terms of the concentration. So as you can see, very low concentrations, but also in terms of reproducibility, retention time, area, very, very good, over 10 replicates within here. So what this allows us to do is to have a very good grasp on things like the calorific value, Wobe index, gas density, etc. All these calculations and measurements that are very important to suppliers and also for the end user, in this sense, most households, to have an accurate reflection of what the calorific value is for their natural gas. All of these come ASTM, GPA, ISO approved. The reporting, the monitoring, trend plotting, all of this is available typically from the process system that you use as well. But very important methods set up. One of the other key areas that we work with is hydrogen analysis. This is becoming very important as an alternative fuel source. So we work with a lot of the nuclear industry with this, looking at traditional hydrogen measurements, but also more recently we've worked looking at the isotopes of hydrogen as well, so to be able to measure deuterium, tritium, and so forth. There's a lot of work and research going into electrolyzers and CO2 reduction and fuel cells, and mainly for things like cars, electric vehicles, hydrogen fuel. A lot of areas, a lot of research looking at this and how hydrogen is developed through these process, as it is for getting things like commercial boilers ready to accept hydrogen from the national platform. And then also looking at ammonia cracking as well, and what hydrogen is giving off from there. So there's lots of areas, lots of research, lots of people having a look at this. And it's very important for the work, obviously, that the micro GC can supply, because we can look at very low levels of hydrogen all the way up to 100%. Hydrogen is a nice one for us to work with in terms of speed of analysis as well, because it comes off very early in the process. So we've got retention times of typically under 30 seconds. So if it is hydrogen alone that people are looking to analyze, we can have run times of 30 seconds, and you can keep a real-time sort of grip on what's happening with hydrogen over a trend of a certain reaction. So as I mentioned, very low detection limits all the way up to 100%. We achieve the lower end of detection by working with argon. So if we consider back to what I mentioned about the thermal conductivity, helium is closer to hydrogen. It doesn't mean that we can't use it. It just means the lower end, we have to consider that we'd maybe only get down to 50 or 100 ppm. If you need to work below that, you would have to have argon as a carrier gas. But the still able to detect obviously very, very quickly, very short run times. And because we don't have any cool down or heat up between runs, this can be performed extremely quickly. In terms of the configurations, this picture, or the one that we focused on so far, is really what we would class as the lab instrument. The other configurations that we supply, which I'll talk about next, which are the mobile and then the process tool, operate exactly the same manner. They use the same analytical channels, same conditions apply in terms of sample pressure and temperature, and being non-condensing. It really is the change to the chassis that change with the configurations. So when we look at a mobile system, because these channels obviously are again very lightweight, we can build them in essentially to a Pelican case. So we class this as a field case. It's anyone that's worked with a Pelican case know the industry standard, very rugged, watertight, crush-proof, dust-proof. These are sent to all sorts of areas out in the field, to offshore. They can be transported anywhere easily because the trolley function with wheels makes it very easy to move around and to lift as well. The system has what we call a kill switch essentially. So the stopper is there that if it's closed, it'll turn off. If it's open, it can start to run. In terms of what the field case offers is not just a house for the analytical channels, so it can take up to 4 channels within here, but it essentially means that you don't have to have any connection to external carrier gas or to power supply. So the field case itself comes built in with batteries. So up to 8 hours per battery within there. And then we've got refillable gas canisters with quick releases. So we can fill these prior to going out into the field with our required carrier gas, whether that be argon, helium, etc., or 2 of the same carrier gas if we need to. And these are basically loaded into the field case. So when we take it out into the field, we've got up to 8 hours of operation. And we just connect the sample to the front of the system. We've got a display on there to see what the column temperatures, pressures, and methodology are set to. And then in terms of the operating software, we connect to a tablet via Wi-Fi dongle, and then you can do all of the running and data interpretation from there. So it allows the user really to take this micro GC anywhere they wish, whether that be in a field, down a mine, offshore. It's ready to go, dedicated case for that. In terms of the other platform that we can offer, so we've got what we call the Pro system, which obviously looks very similar to the lab system that we saw on the previous slides. The main difference between this is that we're using this as an online at-line analyzer. The laboratory instrument is typically used more for research. So people that maybe want to change the samples they're doing, they may want to change column chemistry. The process system really is designed to run 24/7 on plant. The difference physically in terms of the hardware for this, although it's not easily identifiable to see, is that essentially the onboard data handling, so it has a computer essentially built in, a board built into the top there, that we download the methods and calibration onto prior to setup. And then once it's set up, we then essentially connect the micro GC to a DCS, so something like Modbus, Profibus. That allows it then autonomous operation from that central DCS to control the results that are coming out and see what to do with those. So the results could go and alarm a certain part of the plant or process, but it can also take instruction from the DCS as well as to what to sample, when to calibrate. All of these things really, so it can essentially just be connected up and used as a dedicated analyzer 24/7, 365 days a year. This can also be built into industry standard enclosures. So we can enclose into a 19-inch rack, so it can be placed into rack alongside other process analyzers. It can also be built into ATEX proof enclosures as well. So anywhere that needs the ATEX spark proof, it can be built, obviously the channels straight into that. And there's no external data handling software at all with this, because essentially, as I mentioned, the DCS does the control. So we download methods, calibrations, and then the micro GC will talk to the DCS directly. In terms of what it can do, controls, alarms wise, these can go off to various ways. So either through analog or digital boards, depending on what it is that you really want the micro GC to be able to control. It can control up to a maximum of 64 relays, so it can have a very, very large amount of information coming in and going out from it. The events can be set up based on what the customer really needs to do or wants it to do. Some of these applications, for instance, may monitor the level of hydrogen every 2 or 5 minutes on plant. If the hydrogen is between, say, 1 and 5%, nothing will happen. If it goes below 1%, it'll trigger a certain event. If it goes above 5%, it'll trigger a certain event. These are all obviously set up individually. And we've got the option for stream selection as well, which I'll come on to the accessories, but we can take multiple streams into the front of here via Vici valves that allow us to sample with one analyzer from multiple parts across a plant again, or a process. All of these extension boards as well, if they are needed, can be mountable on industry standard DIN rails as well, as can all the accessories, which we'll see in one of the later slides. Calculations I've already sort of mentioned in terms of the calorific value, which is obviously one of the key areas, but there are other calculations that are built into the software, things like LPG, combustion, but also anything bespoke. So if there's a specific need for a customer that they want to work on in terms of something like depth pressure calculations, it may be something for their process that they want automatically converted. These can be done through the software and the third party that we work with for the software to make those part of the process. With the Pro system, there is an optional touch screen on here. It is included in the mobile case as well. It's optional with the Pro because sometimes people like to be able to walk past the analyzers and see what it's actually doing. This won't give chromatograms out, but it will give calculations out. So if you've set it up for something like calorific value or another calculation, it will have the numbers displayed on the screen. But obviously, all of the information is going to a DCS in this instance, whereas this display would show real-time information of column temperatures, pressures, and then obviously any or the last result that's been found. So in terms of control software for the micro GC in general, obviously, like any software, we want this to be simple for the user to interface with. Results need to be clearly accessible. It needs to be able to handle a lot of things, certainly if it's going to be used more as a process tool. So things like sequence tables, calibrations happening automatically, but also to be able to extend the capability from the sampling side. So things like the stream selectors, external sampling devices, handling all of this data and communication that it generates from its system. So there are a few options that we've got available for software. Agilent obviously supply OpenLab, which is more of a general package. It's not dedicated for the micro GC. So we tend to opt for really either one or two platforms for the software. Agilent have a dedicated one for the micro GC, which is called the Pro Express. So we tend to use that one for the mobile platform or for a process system. The one we tend to work with for the lab instrument, but also for process, is called Soprane. So Soprane 2 is developed by SRA Instruments, who are our partners in France and Italy, and they look after the Agilent Micro GC for that territory. They developed Soprane specifically for the Micro GC to get away from essentially open lab that wasn't really functionally wise set up for the Micro GC. So we'll take a look at some of these screenshots on here just so you can have an idea as to what we're talking about. But in terms of configurations, it's very easy. You set up your analyzer initially to communicate via the IP addresses, and then it will automatically detect what channels, what configurations you've got on your system itself. This is where you would choose the carrier gas that you wish to have for each of the channels, and whether you've got a stream selector or a single sample inlet on there. We then have a status page that will show us the various stages and heating portions of the process. So what we've set the heating injector to be at, what we've got the sample inlet to be at, what the pressure of the column and the temperature of the column, and then obviously the detector as well. This one is showing a two-channel system, but if you had 3 or 4, you would obviously see each of those within the same screen as well. In terms of methods, they are very, very straightforward, and most of the methods are already set either from an application note that we've produced, or if it's one of the analyzers like the natural gas or the refinery gas analyzers, these would already be set up for you. But in terms of common parameters, it's always the same. So we look at a sampling time. So on here it says 20 seconds. Typically it is between 20 and 40 seconds that we would sample. And what this means is how long the pump is activated for to actively draw in the sample from the supply, whether that be from a stream selector or from a manual injector or from a continuous stream. So we're essentially pulling through fresh sample for a period of time of 20 or 40 seconds so that it flushes through the analyzer. It fills the sample loop so that we know once we've done it for this period of time, we are working with fresh and representative sample. Within there, we will set the sample injector typically to about, the sample inlet to about 90 degrees. Then we select our runtime based on the methodology. So this could be something like 30 seconds if it's just hydrogen we're looking at. If we're looking at a system like we've got here that is for natural gas, it typically is going to be 180 seconds, so at the higher end of the runtimes. And then for each of these individual channels, we will set individual settings based on what it is we're trying to look for on these channels. So we will set an injector heater, we'll set the column heating, and then we will set the injection time for the sampling. So what portion and how much sample we want to put through from that sample loop. And then obviously the column pressure. If there is a back flush on there, what it is we're going to set and how long for, and then obviously having the detector on. It's very simple setup. Then we simply send that to the analyzer, and then we will start to do our setup in terms of backflush. So if we are backflushing, we have to do a bit of trial and error to work through where the optimum period is of getting rid of something, for instance, like CO2. So if we wanted to get rid of CO2 or methane from the column, we will look to analyze it, see where it comes off, and then we set that backflush time accordingly to say that on that particular channel, we don't want to see that portion of the sample, but we'll look at everything from there. Once we've set up the backflush and the methodology, it's time to do a calibration. Typically, you will calibrate, obviously, for the gases of interest that you're looking at. If you're looking at multiple gases within there, you obviously have to have a known amount of each of those to be able to identify the peak and integrate them so we can see where the retention time is. You can choose to either do one level. If you are looking at quite a wide range of sample concentrations, you may want to do different levels within there so that you have a low, say, ppm sample, then a mid percentage, then a high percentage. But this is really down to the customer. But once the calibration's set up, that's saved within there. And we then get on to the results where we will generate, obviously, very quickly the analysis and the output of the compounds that you're looking to analyze. What we can also do very nicely in this software is to do what we call trend analysis. So previously, this was quite difficult if you were looking at a lot of data over a long period of time. You would have to manually export this into Excel and do the plotting yourself. With Suprain, one of the really nice features of this is to plot these trends almost immediately. So you select the results you've got, whether that's over a period of a day, a month, a year, and then it'll identify the compounds, so whether that's hydrogen, nitrogen, oxygen, etc., that you're looking, and you can see how that changes over time. So if you're doing reaction monitoring, this can be very important. If you're looking at feedback from a process, you'll be able to identify spikes or drops in these certain components. So it's a very, very nice tool to be able to quickly get information and an overview of what's happening within your sample. In terms of sampling accessories, the more common ones here we sort of supply. The first one looking at is a Genie filter, and this is really to protect the analytical column against residual moisture particulates from there. Obviously, we want to condition our sample so it's dry and non-condensing before it's coming in, but the Genie filter will capture anything within there via a membrane, and then it will feed into the pressure reducer. Is obviously, as it suggests, is to be able to drop down pressure to the required limit. So you can set this between 0.5 bar and 1 bar. Typically, we go in the middle of that at about 0.7 bar. So there's just a needle valve on the side. So your sample line will come into the pressure reducer. You will set it to the required level that we want to be able to deliver it to the micro GC. The excess will be passed to vent, and then the sample will obviously be introduced, often via the Genie membrane still, and into the front of the analyzer. We have the option to do manual injections, as I've alluded to in a few of the other slides. So if you've got a continuous sample, you're obviously connecting that up from a line, and you're sampling when your method tells it to start. If you haven't got a lot of sample or you've collected it offline, you've obviously got the option here to inject. So you can do this by connecting up a syringe, whether that's just a standard syringe or via Lua lock. Within there, you've got the option for both. This accessory that we show here is actually quite nice, because on the previous models, you used to have that manual injection straight on the front, where we can see the A within here. You would have to switch between continuous and manual by taking off this front end port. This accessory now has a two-way valve on it, so you can switch up to sample manually or switch down, and it will put it into continuous mode for you. So it's a little bit easier and more compact solution. We've got a micro gasifier to work with LPG, LNG samples. So this is a pressure drop down system, so it can handle the higher temperatures, higher pressures, condensing samples, and then it'll deliver it at the required level to the analyzer. We also have, as I mentioned, the ability to put on stream selectors. So these are Vici valve, industry standard valves. We can cascade these to have up to 3 of these valves on at once. They can be flow through or closed, but typically we work with the flow through options. And really, they come in a variety of configurations to meet the needs, whether you want to go with 6, 8, 12, 16 positions within there, whether you want to connect up a reference gas or a calibration gas within there to periodically put through as well. All options are available from there. And all of these accessories come nicely mounted on a bracket, so it's a very nice solution for us. There are other options available in terms of sampling. So if you have very low sample volume, that can often be an issue, because we need to have a certain amount of sample to be representative through the system and a certain pressure to come in. There are options that we can work with third parties to help with this as well, whether that's introducing a sample pump or a dedicated system to build the pressure up for us. Essentially, anything that we need to do for conditioning beforehand, we're available to discuss this with the end user. So in terms of drawing this to a close, in summary, obviously analysis time for gases now is cut to seconds. So obviously benchtops maybe take 20 minutes to do this. Other analyzers may take longer, or certainly higher minutes. But the micro GC is an incredibly quick platform for gas analysis, very reproducible. We've seen that from the data, and obviously the platform itself has been around for 15 plus years. The 990 itself is just the latest iteration of it. Very compact footprint, both physically and environmentally, which means we can do lots of things with the system, whether it be in the lab, out of the lab, or on plant as well. Industry standard, so obviously Agilent have worked very hard at getting this into the relevant sort of bodies like ASTM, ISO, etc., to make sure that it's ready to meet all the demands that it needs to for your work. And future-proofed flexibility, certainly with the way that the 990 has been designed now, that the channels themselves are not only interchangeable in terms of the components inside, but also in terms of removing them and replacing them with channels as your needs change. This is something the user can easily do due to the design of the 990 as well. So essentially you can start with a single channel system which can be built up to 2, 3, or 4 if needed, or you can interchange your channels based on the need or the requirement at the time. So hopefully you've enjoyed that quick run through there of the micro GC. We've obviously got a Q&A session coming up now if we do have anything that wanted to be covered during there. The recording will be available and sent out to anybody that requests it. So if you do want the recording of this, just pop it in the chat or the Q&A box, and we'll follow up with that to get that out to you. I'll just leave it for a minute to see if we've got any questions. So we've got one question here. Can you quantify the disparity between thermal conductivities, or is it just an inert gas which is as far from the conductivity that you want to measure? Yes. So we obviously know the thermal conductivity of the carrier gases that we're going to use. So typically it is limited to helium, hydrogen, argon, and nitrogen. We do have the option for some other applications, and one recently has been neon, where we were looking at the isotope analysis of hydrogen. But obviously we quantify that on a known thermal conductivity. So when we are measuring the gas that has the sample and the carrier in, we know that we can subtract the carrier gas thermal conductivity from the result, which is what gives us this disparity and the ability to basically detect the analytes within there. Don't think we've got any more within there. So with that in mind, I will draw this to a close and stop the recording. Thank you all again for joining us today. We look forward to seeing you on the future ones. Enjoy your day, and thank you very much.